What the heck is this picture over here? Well, this is an actor, Rex Harrison, who played in this movie. Oh, you mean this thing? This animal is called the push me, pull me. And he's a perfect example of a free body diagram. This animal, you might say, hey, if both of them push at the same time or pull at the same time, how far are they going to go? Well, they're not going to go anywhere. But I don't think it's going to live long because this digestive system, it goes in, I don't know, there's something creepy about this critter. Well, let's use him as a metaphor for these free body diagrams. We could pull 80 newtons to the left and 100 newtons to the right. That seems kind of counterproductive because I think you can see that the total force left over is only 20 newtons to the right. They're not contributing evenly. Oh no, it's stuck. The slideshow has stuck. On the lower one, it says 80 newtons to the right and 100 newtons to the right. There it goes again. And this adds up to 180 newtons to the right. So direction of force really matters. So the purpose of a free body diagram is just to resolve all the forces. The term resolve, resultant, these are vector terms. When I say let's resolve the forces, I'm just saying add them all up. It's like the difference between the word velocity instead of speed. We're trying to indicate by our terminology that don't forget the direction. This object has a force pulling up and a force pulling down. So the sum of all forces needs to be worked out first. This little thing here is called sigma, and it's a Greek letter meaning sum. And it's probably on your calculator if you go looking for it. So you take the sum of all forces as F1, F2, F3, and so on. And they are definitely vectors. Okay? Once you get the sum of all forces, then and only then can you calculate the acceleration using the total force that's left behind. You don't get two accelerations on an object unless you're ripping it in half. So you must resolve the forces before you can use Newton's law to calculate the acceleration. Let's take a quick example. If I set the upwards force at 100 newtons and the downwards force at 150 newtons down. So 100 newtons up, 150 newtons down. We'll call up positive and down is negative. F net. What the heck is F net? I thought you said to use sum of F, Kaladi. Same thing. This is one way of writing it. This is the other. I think you'll quickly find you'll prefer the sigma notation. Writing F and a little net in your notes, it gets crowded. So getting rid of the direction and changing it to integer notation, positive 100 added to negative 150 equals minus 50 newtons. Minus is down. There's our answer, 50 newtons down. So 50 newtons down is our total force. Now we can put it into Newton's equation, divide by the mass, and we get our answer of 5 newtons per kilogram down. Now what the heck is a newton per kilogram? Acceleration is supposed to be in meters per second squared. Ah, yes, grasshopper, you shall see how it is in fact the same thing. Let's move on. Here's what our expectation is. When we calculate acceleration, we were expecting to see units of meters per second squared. Instead, the formula gave us newtons per kilogram. Are these the same thing? Let's do a trick called dimensional analysis. Okay, so I'm going to go ahead here and write F over m. That's supposed to be acceleration, but it gave us newtons per kilogram. Let's remember, newtons mean something. A newton is a kilogram meter per second squared. That's what it is in fundamental units. And notice the kilograms will cancel, leaving us only with meters per second squared. So in fact, a newton per kilogram is the same thing as a meter per second squared. And you will find that there are times keeping acceleration as newtons per kilogram makes a lot more cranial sense. You'll be able to understand what's going on better. So these two are in fact equivalent, and I would be quite content if you wrote accelerations this way on the unit test. Let's try a simple example. We have 100 newtons up, and I'm telling you the total. I'm already giving you this. What I haven't told you is this one, but if I've given you the net force already, then you can actually calculate the acceleration right away. So we don't have to resolve the forces now. It's been done for us. So we put in our net force, stick it in the equation, divide by mass, and we get 2 meters per second squared, or 2 newtons per kilogram down. Now, 20 newtons down is the addition of plus 100 plus another number. What can you take to 100 and add to it to get an answer of negative 20? Well, written out long form, it looks like this. So F2 is the total minus F1. F2 is 20 newtons minus 100 newtons. Minus 20 minus 100, we get an answer of 120 newtons down. Does that make sense? Does 100 up and 120 down actually equal 20 down? Yes, it does. Here's the third example, and this is the one that gets the hardest. You got to remember, this is calculated from the individual forces. This is the behavior we're going to see. For some reason, if I write F equals ma, everyone knows what to do. But the minute we write this one, sum of forces equals F1 plus F2, for some reason, students forget this side here. Okay? So let's say I say a mass of 10 kilograms accelerates at 10 meters per second squared, and I'm telling you F2. So I'm giving you the acceleration, but I'm only giving you one of the forces. I'm giving you this force, and I've told you A, but I have not told you the sum of forces. But in fact, the sum of forces is related to A. You've got 2 ways of dealing with this. And for some reason, once you do this way, students suddenly forget this way. It is so common to see that. It is just crazy common. It is the most common mistake I see. I don't know what to do now when you gave me the acceleration, but not the total force. A times m, and you got it. So how do we do this now? Simple. The sum of forces is in fact m times a. 10 kilograms times the given acceleration, we get 100 newtons down. So we've already got 100 newtons down is now the total force. And we were told that this one here, F2, was 300 newtons down. So 100 down came from 300 down plus what? I think by inspection you could see 200 up, 300 down gives me 100 down left over. And this is the one, it's not any harder than the others, but is just caused by students forgetting that the sum of force is equal to ma once they see this part. And that's it for right now, and we can go on with some examples together as I unelegantly end the show.